Hi everyone, welcome back to Mathematics 0110. This video is about something called asymptotes. We're going to look at two different types of asymptotes, vertical asymptotes and horizontal asymptotes, and they're both features of graphs that can be defined in terms of limits. Part of what we do inside this section is we talk about infinity, both as an outcome of taking a limit and as an input into a limit. So when we think about limits we were doing before, we were looking at, let's say, limit as x approaches 3, or limit as x approaches 0, or limit as x approaches -10. We will, inside this section, in the discussion of horizontal asymptotes, we'll be taking the limit as x approaches infinity. So that's one side, that's one piece. Another piece is another examination of this idea of division by 0 causing a problem. And we're going to make a distinction between divisions by 0 that cause the resulting calculation to be DNE, does not exist, or infinity or minus infinity. We're going to make a distinction between those three different types of problems that can result when we divide by 0. As a reminder of that exact scenario and where it happens, we have a limit like this one. Limit as x approaches 1 of x plus 2 divided by x minus 1. So when we attempt to plug in 1, we get 1 plus 2 over 1 minus 1. So we get 2 over 0, which we've been saying up until now is DNE, does not exist. Let's look at what happens if we take the limit from the left of 1 and from the right of 1. So I'm going to write this as a separate example. What is the limit as x approaches 1 from the right of x plus 2 over x minus 1? So on top we're going to get, oh sorry, I changed this to, my apologies. I changed this x plus 2 to an x plus 1 for no reason. So this is 1 plus 2, this is a 3, 3 over 0 still doesn't exist, doesn't change the answer. Might as well fix it. But for the next one, when x approaches 1 from the right, we're going to get 3 on top. And in the bottom, we're going to get 0, kind of. We're plugging in a number a little bit larger than 1. So you can imagine plugging in 1.00001. So yeah, in the denominator, you have 1.00001 minus 1. So you're going to get 0.00001. It's essentially 0, but it's positive. Now this notation is not standard. You are not supposed to write, and I'm not supposed to write, and nobody is supposed to write 3 divided by 0 plus. What we're supposed to do is we're supposed to skip writing that step and just say the answer is infinity, which may look confusing. We get out a calculator or use an online calculator and look at what happens when you plug in a number like, let's say, 3 divided by 0. I'll pick something not too small, 0.01. And the output of that calculation is 300. Let's make it even smaller, 0.01. Now it's 3,000. And as we get closer and closer to 0, I don't want to do that there. So 0, 0, 0, we got 30 million. As the denominator gets smaller and smaller, so as we divide by a smaller number, the outcome of the calculation gets larger. So 3 divided by 0 plus, that's positive infinity. We can make this number as large as we want by making the denominator get sufficiently close to 0. What happens if we take a negative side limit, a limit as x approaches 1 from the left? Limit x approaches 1 from the left, x plus 2 over x minus 1. Well, this is like, I should write this stuff down, 1 plus is like 1.00001. It isn't 1.00001. This is how you can think about what 1 plus means. 1 minus is a number a little bit less than 1, it is like 0.99999, etc. So when we plug that number in, look at what happens. We get 3 on top still, or if you want, 2.99999, but I'll put 3. And the bottom, we get 0.9999999 minus 1. So a number smaller than 1, minus 1, we'll get something negative. It's essentially 0. It's as small as we want it to be, by making x sufficiently close to 1 from the left. So instead of saying division by 0, I'll say division by 0 minus, just to indicate that this isn't necessarily going to be the same outcome as what is above. Like, what if in the Desmos window I change this to a minus 0.001, I get minus 30 million. And as I make this more and more negative, or if I make this closer and closer to 0, which I guess means less negative, I make this closer and closer to 0, the result of the calculation gets larger and larger and larger. Or rather, more negative, I should say. Keep messing that up. Sorry about that. So this would be minus infinity. But what does this graph look like? The original function, x plus 2 divided by x minus 1. X plus 2, x minus 1. So this is what the graph appears to be. So let's make sense of this picture and the algebra we have over on the right-hand side. We have a vertical asymptote, a place where the function explodes to plus infinity or minus infinity, which was our definition of vertical asymptote from the beginning of the course. To the left of the vertical asymptote, so let's see where it is. It looks like it's happening at 1. That's where the denominator is equal to 0. To the left, the y value is getting more and more and more negative. So imagine drawing a math car there and pushing the math car to the right towards an x-coordinate of 1. The y-coordinate goes lower and lower and lower and lower towards minus infinity. It keeps going down forever. And if we look at the limit from the right-hand side, so you put a math car over to the right of x is equal to 1 and then push it towards an x-coordinate of 1, what does the y-coordinate do? It gets higher and higher and higher. So this analysis is matching up with the graph, as it must. So we're going to use this idea of what limits are doing to define vertical asymptote. So this is just recycling the definition we had before. We'll say that the limit as x approaches c of f of x equaling infinity and or minus infinity is the definition of x equals c being a vertical asymptote of f of x. So if told that there is a vertical asymptote at x is equal to c, then one of these two things, or one of these two things must be true. Limit as x approaches c of f of x must be plus infinity or minus infinity, or so put or limit as x approaches c from the left of f of x is equal to infinity, or limit as x approaches c from the right of f of x is equal to infinity, or limit as x approaches c from the left of f of x is equal to minus infinity, or limit x approaches c from the right of f of x is equal to minus infinity. So if any one of these things is happening, if we're getting a plus infinity or minus infinity as a result of a limit from the left, a limit from the right, or the two-sided limit, or any combination of those, then we can say that x equals c is the location of a vertical asymptote. That's our definition. So another example of a function that has this type of behavior is f of x equals 1 over x. It has a vertical asymptote at x is equal to 0. If we take the limit as x approaches 0 from the left of f of x, we get minus infinity. If we take the limit as x approaches 0 from the right of f of x, we get plus infinity. What I want to warn you about is using the fact that there's a 0 in the denominator as an indication of a vertical asymptote. I want to warn you that this is sometimes wrong. You can't just say 0 in the bottom, whatever x value causes that is also the x value where the vertical asymptote is. That's not necessarily the case. In the blue box here, x squared minus x all divided by x, that function, the denominator is 0 when x is 0, but that's not the location of a vertical asymptote. It's actually the location of a hole. If you common factor an x on top, the x on the bottom, cancel them, you get x minus 1 on top. Limit as x approaches 0 of that is negative 1, which is not infinity, and it's not minus infinity. And recall from previous lessons that this is the hallmark of a hole. If the value of the function, so f evaluated at a, gives you dn e, but the limit as x approaches a of f of x actually gives you an output, then there's a hole at that x coordinate. So I'm going to add the definitions to this slide. This is a slide that will get posted online. So I'll put or limit x approaches c from the left of f of x is equal to infinity, or limit x approaches c from the right, no, c from the left of f of x is equal to minus infinity, or limit x approaches c from the right of f of x is infinity, or limit as x approaches c from the right of f of x equals minus infinity. If any one of those things is true, then we have a vertical asymptote. Okay. Find the vertical asymptotes of this function. F of x is x plus 5 over x minus 5. Now, I'm not going to take the left and right limits of each of these. What I'm going to do is I'm going to say, as a type of shorthand, when you take the limit as x approaches a of f of x, if you get something that's not 0 on top and something that is 0 on the bottom, as a shortcut, we can say that the function has a vertical asymptote there. So here's the shortcut, I'll write it down. If the limit as x approaches a of f of x, if that limit equals not 0 divided by 0, then x equals a is a vertical asymptote. Just a quick way to do things, and if we apply that rule here, we have to think about what value of x causes 0 to happen on the bottom, and that would be x is equal to 5. So I'll say x equals 5 is a vertical asymptote since limit as x approaches 5 of f of x equals 10 over 0, which is not 0 divided by 0. That's it. So the answer is x is equal to 5. Let's do the same procedure for these 4 problems. So top left, when is that one going to be not 0 over 0? we want not 0 over 0 for vertical asymptotes. X equals 1 and x is equal to -1. Plug in either of those, we'll get 1 or -1 on top and 0 in the denominator. So that fits our shortcut for the locations of vertical asymptotes. Okay, one down below. When do we have not 0 over 0? Want not 0 over 0 for vertical asymptote. X is equal to 3 and x is equal to -2. Just making sure we double check that the top is not also 0, either of those x values, and it's not. Okay, I'm going to save the top right for last. I'm going to do the bottom right next. Our goal is we want not 0 over 0. And when does that happen? It only happens at one x coordinate. X equals just going to add some language to this, are the vertical asymptotes, just so it looks like a proper conclusion. So here it's just 1, x is equal to 2. It's the only vertical asymptote. Don't get distracted trying to solve the top being equal to 0. Just solve the bottom being equal to 0 and then double check that those x values or that x value does not also make the top 0. Don't do extra work. Okay, now top right, it looks like the answer would be 2 and -2. Let's see. And neither of those will cause problems with 0 being on top. Want not 0 over 0 for vertical asymptote. X equals 2. X is equal to -2. I put a little check here. Check. Or maybe confirm. I'm going to confirm f of 2. I'll do limit as x approaches 2. Limit x approaches 2 of f of x is equal to 4 plus 2, 6, minus 20, -14 over 0, which is not 0 over 0. So that one's good. And we can confirm limit x approaches -2 of f of x. So we have 4 minus 2, so 2 minus 20 minus 18 over 0, which is also not 0 over 0. Okay, so those are the two solutions. So I'm going to circle the answer for each of these, and I go to the next set of examples. Okay. In addition to having functions with denominators, so rational functions, having the potential for a vertical asymptote, another type of function that can have a vertical asymptote is a log function. So log base b of x has a vertical asymptote when x is 0. Log base b of x minus 3 has a vertical asymptote when x is 3. What's going on is every time the argument of the log function, every time the part being plugged into the log function goes to 0, then the log function is going to have a vertical asymptote there. In truth, it's that whenever the argument of the log function goes to 0 plus, then the log function will have a vertical asymptote. If it's negative on both sides, so if the argument is going to 0 but 0 from the left, then that does not mean that there's a vertical asymptote there. It means that you're at an x-coordinate that's not in the domain. So that's one other type, log function. So we have rational functions, which were these ones. So rational functions can have vertical asymptotes, and now log functions can have vertical asymptotes. There are other types of functions that can have vertical asymptotes, including trig functions. So shown in the bottom graph here is tan of x. It has vertical asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, and every other similar multiple of pi over 2. There's more. There's more than that. There's also arc functions, arc sine of x. I guess arc tan. It's arc tan, not arc sine. Oh, hey. So, oh, what are you doing? Arctan has a horizontal, I'm sorry. What was I thinking? Oh yeah, secant. Secant of x, which is 1 over cos, has vertical asymptotes. And then cosecant of x, which is 1 over sine of x, has vertical asymptotes. And cotan of x, which is 1 over tan of x, has vertical asymptotes. And then there's more than that. So I'll leave it there just to say trig is not part of this course. I at least just want to mention that there are other function types that have vertical asymptotes other than rational functions, where the bottom is 0 and the top is not 0, and log functions, wherever the argument goes to 0 plus. Okay. I think there's some examples with logs later, maybe? No. Okay. I'll add an example right now. So I'll put it in this little box here. Example. Where does f of x equals log base 3 of, let's see, 1 minus 3x have a vertical asymptote? So where does that happen? Where does this function have vertical asymptote? So we want 1 minus 3x to go to 0 plus. So 1 is equal to 3x. That means x is equal to 1/3. So vertical asymptote at x equals 1/3. Basically set the inside equal to 0 and make sure that at least to one side of that number, the log function is going to be 0 plus. It has to be positive. Okay, so that's part 1 of this section. I'll talk about infinite limits in the next video.